In this presentation, I'm going to describe what the cumulative distribution function, or CDF, is, the probability density function, or PDF, is. I'm also going to describe how they're related, and then how you can also use these two functions in order to compute probability. So first, let me define the cumulative distribution function. The cumulative distribution function, again, CDF, can be defined mathematically as the function of x. Note that this is an uppercase F, and this x is our random variable. This term is equal to the probability of our random variable being less than or equal to some constant value of x. So basically, the CDF allows us to directly compute the probability at some point on a line, or at some point on the function. The PDF is mathematically described as the function of x. Again, note that this is a lowercase f. Again, this is our random variable. As the derivative of d f of x with respect to x. So this, again, is our CDF. So basically, this is telling us that CDF and PDF are related through a derivative. So how can we ultimately solve back for f of x so that we can use this to get back to that probability? We take the integral. So what we find is that f of x, again, this is our CDF, can also be described as the integral from negative infinity to x of the PDF. In this case, we're going to use a dummy variable z. So f of z dz, and this is our PDF. And all of that is equal to this. So what we can do is we can solve for probability using the relationship between CDF and PDF and the way that they're defined mathematically. So let me show what this looks like using a graph, because I think it'll give you a better idea of what these functions, how the functions are related, and then also I can use it to show you specifically how to calculate the probability. So the first thing I want you to note, here, let's find a brighter color, is that this line up here is your CDF, as you can see here, and this line down here, so this function, is your PDF. Now this graph is a graph of an exponential random variable plot. So you can see that the PDF is essentially the slope of the CDF, which we already knew mathematically because the PDF is equal to the derivative of CDF. So from a graphing standpoint, we can prove that, because we see here at a high slope, or a high rise over run, the value for PDF is high. And when there's a small slope or rise over run for the CDF, we find that the value for PDF is low. Now, based off of the relationship, we know that if we pick any point on this line and we take it down, wow, that's a bad line. That's a little bit better. We know that the PDF is the integral of the CDF which is the area under the curve, and since, so this area under the curve, and since values for our random variable are greater than 0, we just integrate to 0. So our integral here tells us what the CDF is. And again, we saw that mathematically because we said f of x is equal to the integral of negative infinity. And again, in our case, negative infinity was just 0 because that's as far as our random variable could go, of f of z dz. So the integral, this, is this part under the curve. And you can see that as our random variable gets larger, the CDF increases because we are looking at a larger area. So at 0.5, we have an area under the curve here at a certain point that translates to some point here, and so on and so forth. And as that random variable gets larger, we see how the area under the curve gets bigger. Okay, so how can we use this to specifically compute probabilities? So I'm going to put that a clean version of the graph back on. And let's say we're trying to find the probability for a certain interval. And let's say we can call that interval from some arbitrary point x1 to x2. We know that that probability is equal to f of x, which is equal to the integral negative infinity to x of the PDF, which we represent as f of z dz. So if we want to, we can just put it in terms of f of x, since all of these terms are related, and we can just say, quite simply, that f of x2, or the probability, so this up here, is equal to f of x2 minus f of x1. Again, because we're trying to find the probability between x1 and x2. So let's pick some value that we're looking for, first of all. So again, I want to erase this and give you something clean to look at. And let's say we want to solve for the probability of x being between 1 and 2. So what can I do? Remember, we've got two options. Option number 1 is to use the CDF, and option number 2 is to take the integral of the PDF. So let's do option number 1. Option number 1 is that we can essentially determine what f of x is at 1 and at 2 and subtract. So in our case, we find that f of x of 1 on the CDF plot is here, which is about 0.6. F of 2 is equal to about 0.8. So what we do is we subtract f2 minus f1 and we get 0.2 as our probability. So what's our other option? The other option, so let me just poorly erase this. The other option is to do the PDF. And in this case, what we can do is we can take the integral, or the area under the curve, of the PDF, which again is this line, from 1 to 2. If we were to actually go in and do that and count this, we would also find that the probability is equal to 0.2. So from this video, hopefully you've seen what the PDF is, what the CDF is, how they are related to each other, and basically how we can calculate probability and use the relationship that exists between PDF and CDF to calculate probability based off the PDF. Thanks.